since these are all subsets, so if A is a event, that means it is in a sigma field, and B also a event, that means B will be in a sigma field. Suppose let us consider in general, suppose S and C. So, S is the sample space and C is the some collection of subsets, like a class of subsets of C, class of subset of S, that is a sigma field that we discussed. Then A union B, by definition of a sigma field, it will be in C. So, it will be a event again, because any element in C, that will be defined as a event. So, then A intersection B, it will be also in C. So, now it is also event. Now, some of the special event, one event it is called impossible event, null event, some of the name. Suppose phi is a null set. So, it does not contain any element. You are throwing a die, 1, 2, 3, 4, 5, 6, something will happen, but phi does not contain any of that. So, phi cannot occur any time. So, that is why it is known as impossible event or null event sometimes. And second is this sample space S, whatever observation it come in any run, it will be inside S, then we say that S occurred. So, that means whatever happened, whatever the random experiment, whenever you do, S must happen all the times. So, it is known as, this is also in C. So, it is a event, it is known as, so this is known as impossible event or null event, some of the name, some other name also there, special event, null event, empty event also it says, the event contains no elements, and S it is known as certain event or some, it is known as inter event, always occur, or inter event sometimes it says inter event also, or certain event it say inter event. So, we also say inter event. There are some other union means in the Venn diagram it is shown, it contains all the elements of A and B, any element, it either it belongs to A or below B, or it may be both, it is known as union. Intersection means it is in the common space. So, that means it is A and this is B, this is the sample space, this is A and this is B, and this part is known as the A intersection B. That means all the element of B that belongs to A as well as that belongs to B, it is known as the intersection. So, another concept it is called the complement of a event. So, complement of a event, how it is defined? So, complement of an event means you consider all the element which does not belongs to A. So, A is any event, suppose let A be event, let, so here we are denoting C is the sample space and C is the collection of a class of subsets of S that form a sigma field, that is the event, and let A belongs to C, that means A will be subset of S. So, what will be the complement? So, we have already discussed that for sigma field. So, complement will be nothing but basically it is shown here in the Venn diagram. So, this is nothing but this is S and this is A, all the element other than the A. So, this is A. So, all element belongs to S such that S does not belongs to S. This is nothing but complement. So, I assume that all these things you know, because in the some of the mathematics courses, basic mathematics courses, you have already learned all these set theoretic things, but because it is required here also, that is why it is repeated in the slides, but I assume that you have already known, that is why we have already discussed A complement for the discussion of the field and the sigma field. Already we have already discussed what is A complement, already used this concept, this is A complement, and also whenever two sets suppose belongs to C, let A B belongs to C, that means it is a event, that means A also subset of S and B also subset of S. So, suppose this is a S, this is A and this is B, such that A intersection B is null set. So, what is the A intersection B? We have already decided. So, all S belongs to A and B. So, here you can see that if it is A and it is B, none of the points belongs to A and both A and both B, both A and B. In that case, if A occur, suppose that means you are doing the experiment and that element belongs to A, then B cannot occur, that element cannot be B because intersection is phi. So, that is why if A occur, then B cannot occur. So, if B happen, then A cannot be happen. So, that is why whenever A intersection phi be phi, that is known as mutually exclusive events. So, here it is written A intersection, two events A and B are called mutually exclusive if A intersection B is equal to phi. So, the extension of this concept, it is known pairwise mutually set of exclusive events. So, mutually a set of events A1, A2, A, it may be countable collections each. So, this is a set, countable collection of set of events is said to be pairwise mutually exclusive events if, so it is called pairwise mutually exclusive set of events if AI intersection AJ is equal to phi for any I not equal to j, I is equal to 1 2 like this, j is equal to 1 2 like this. This is called the pairwise mutually exclusive set of events. So, pairwise mutually exclusive and exhaustive set of events. So, this is another definition, this is very important, later on we will discuss this again. So, pairwise mutually exclusive and exhaustive set of events, a set of events A1, A2 like this is said to be pairwise mutually exclusive and exhaustive set of events if AI not equal to AJ. So, there are two conditions because mutually exclusive, pairwise mutually exclusive, AI intersection AJ, first condition is phi if I not equal to j, I is equal to 1 to n, j is equal to 1 to n, sorry not n, it will be infinitive countably. And second condition is that, so first condition is that they are pairwise mutually exclusive events. The second condition is that if you take the union A1 union A2 like this, so basically we denote just short notation I is equal to 1 to infinitive AI, this will be nothing but S. So, this is nothing but it is like a partition of a set. So, suppose this is the S and you just take a disjoint collection. So, this is suppose A1, this is A2, A3, A4, A5, A6. So, they are pairwise mutually exclusive, and if you take the union of them, then this will be nothing but S. So, it may be countably infinite or it may be some finite number of sets also, two sets also, just here in general I discussed. So, it may this may be considered as finite collections also, it is pairwise mutually exclusive and exhaustive set of events. So, so whenever it is finite collection, then we will discuss just this is a set of events A1, A2, An is said to be pairwise mutually exclusive and exhaustive set of events if this is not equal to phi, and then this is union of An. So, I is equal to 1 to n Ai, this is equal to S. This is the example actually I gave here, this is finite collection only. So, this is mutually pairwise mutually exclusive and exhaustive set of events. So, okay. So, these are the some of the important concepts we discussed, definition of sample space and also definition of events. Whenever we learned it, we understand it clearly. Next, we will discuss what is probability. Now, we need to the position of defining the probability. So, next let us start the discussion of probability. When scientists started defining probability, there are several approaches came out, because some of the approaches for defining probabilities were not widely accepted by all the scientists. Some of the approaches we will discuss. Finally, the probability, it will be defined by axiomative approach, where mathematician always define by the axioms. Here at the beginning, some of the approaches we will mention here to understand it, how probability it was defined at the beginning. It is known as classical approach. If some of the assumptions are correct and it is assumed or it can be considered, then this definition works well. But problem is with those assumptions, we will discuss slowly. First, let us discuss classical approach. What is classical approach? So, this is usually we understand what is probability. Usually, so whenever we want to find a probability like this, suppose there is a box or urine, we say, and there are some balls. So, there may be 6 black balls and 4 white balls, and this is mixed properly such a way that chance of coming out the ball, any ball, are equal. There is no partiality to the one balls, that ball can be come out more likely than the other balls. So, that is called the equally likely. So, in this approach, it is defined like, suppose you are drawing a ball, and that ball, what will be the probability that it will be white. So, classical approach says that if there are n possible ways, those are equally likely to happen. Out of that, the probability what we want to consider the event, that is the white ball it come out, how many possible way this event it can come. Like white ball, there are 4 white balls, total 10 way ball can be drawn. Out of that, 4 balls white can be, so 4 way that the white ball can come out. Then the probability that the white ball, probability that the white ball can appear, this is nothing but 4 by 10. So, this is 0.4. This is the classical approach. So, let us see that classical approach, if an event can occur in h different out of total n possible ways, all of which are equally likely, then the probability of the event is h by n. So, this is n possible way, n is nothing but it is represented as n total of n possible, total number of possible ways, and age is nothing but the event can occur in age different ways. The event can occur in age different way. So, then the probability that this event A is nothing but h by n. So, here we have already discussed one example that this is 0.4 probability, because 4 is the age is 4 here and n is nothing but total number of possible ways is 10. The problem is that this concept of equally likely, this terminology, this term it is not it was not widely accepted by all the scientists. The reason is that when we are defining a probability, the possibility, the probability, equally likely it seems like it is also some name of the probability. Equally likely, what does it mean? Equally likely means you are saying that equal probable, all the ball can come equal probable. So, that definition itself contain that term. Also, how you know that this is equally likely or not? Even if you can assume that things, there may be it is not mixed properly, or some balls are bigger than, some balls smaller. So, in that case it will not be equally likely, then what you will do? How you will find this probability? So, this equally likely term, it is vague and all scientists could not accept it, this definition. For finite number of balls it is okay. Now, suppose you have a coin, you are tossing a coin and both sides you do not know it is equally likely or not. You are tossing a coin 10 times and you see that head appear more, it will not be exactly pipe and pipe. And if you toss the coins 100 number of times, maybe you are seeing that 80% times this head occurring. So, then it is not equally likely. In that case, how we can compute the probability? Then this frequency approach it came for a frequency approach for defining the probability. Frequency approach says that you repeat the experiment n number of times, where n is very large. So, you repeat the experiment. So, here it is, you can see that if after n repetition of an experiment where n is very large, an event is observed to occur in age of this, then the probability of the event is h by n. So, n is the, so there are two conditions, n is very large, n is you repeat the experiment n number of times, n times, and the event occur. So, the notation it is used, the event is observed to occur in age of this. The event is observed to occur, event is observed to occur in age of this, occur in age of this. Whenever n is very large, then the event, suppose we denote by a, event a, then probability of a is nothing but h by n. For example, you repeat tossing a coin, suppose n is equal to 100 number of times, and you observe age is equal to some 55. So, then your probability of a is nothing but h by n, this is nothing but 50 by 100, this is 0.55. Suppose you want to repeat your experiment more number of times, 1000, and assume that age is equal to some 665. Just I am assuming it, you repeat, then your observation is nothing but 1000, this is 0.656. Note that you may not get the 0.55 always. So, then you repeat more number of times. Now, question is, whenever you are saying n is very large, then which n is very large? N is equal to 100 or n is equal to 1000 or n is equal to 10,000 or more number. So, this n is equal to very large here also it become vague to the scientists. All the scientists could not accept it, because when it should be stopped, whether it will be a converging or not, we do not know, and in which value we will consider, in n which n values it will be considered. Basically, we do not know that which n values it may be considered as a very large. That is why this classical approach also it was not accepted. So, these are the drawbacks, that both the classical and frequencies approaches have serious drawbacks. The words equally likely are very vague in the classical approach, and the large number n is very large number also involved is vague. So, mathematicians have been led to an axiomatic approach to probability. So, to defining the probability. So, usually mathematicians define something by axiomatic approach. So, axiomatic approach means we will assume some minimum number of rule, if by that function or something it satisfied, then we define that will be the probability, like that. So, that minimum number of rules we will not going to prove, it is that we say it is a axiom, if it satisfied by that function, then it is a probability. And then some other, many other whatever properties if you use by that function, we have to prove using the axioms. So, let us discuss axiomatic definition of probability. So, hope you have understood that what is classical approach and what is frequency approach, what are their drawbacks, and why you are going to define it, the axiomatic approach. So, in the axiomatic approach, suppose we have a sample space S. We have a sample space S. If S is discrete, we have already discussed that you can consider all subsets of S as a events. But if S is continuous, if it is not non-discrete, then some special subsets. So, in a sigma field, we have to consider that sigma field, here it is called a measurable function, measurable sets. So, all the elements in the sigma field also known as measurable sets. So, it is a part of measure theory, we will not discuss more, we just discussed that sigma field also. So, here we will consider S be a sample space, let for a random variable, let S be a sample space associated to a random experiment and C be a class of subsets of S, C be a class of subsets of S, C be a which is a sigma field also. C be a classes of subset spaces is a sigma field. Let us write class of subset of S. So, satisfying, so that means it is a sigma field satisfying the following conditions. So, first of all S belongs to C. If A belongs to C implies A complement belongs to C. We have already discussed those things. If, so we write if A1, A2 some countable collection belongs to C implies union of AI belongs to C. So, that means C is a sigma field. So, this is the, so we consider here this is the in the axiomatic definition. Now, for any A belongs to C, for any A belongs to C, we define a function P. This is actually C to R. So, okay, actually we assign actually sorry. So, basically we have to see. So, we should write in this way, let P C to R be a function, that means for any A belongs to C, basically A is a subset of S, we assign a real number P A. For any A belongs to A C, then real number P A. So, P is called the probability function and P A is the probability of A if So, P is we assign the real number this, P is called a probability function and Pa is called the probability of the event of event A if it satisfies the following conditions. First condition is that, so all the things it is written here more clearly. To each A in the class C of events, we associate a real number Pa. The P is called a probability function and Pa the probability of the event A if the following axioms are satisfied. So, if the following axioms are satisfying, first is that for any A belongs to C, P of A will be greater than equal to 0, S always belongs to C. So, S for S, P of S is equal to 1. So, let us write 1, 2, 3. So, this is 1, 2 and 3 is that if A1, A2 like N are pairwise, so mutually exclusive set of events. So, infinite collection. So, it is countable infinite pairwise mutually exclusive connection. So, that means AI intersection AJ is equal to phi I not equal to j. Then so whenever A1 A2 N mutually exclusive pairwise mutually exclusive events. So, because it is a field union of I is equal to 1 to infinity, this is a event actually. So, this will be belongs to C again. So, we can talk about what will be the probability of this. So, this probability will be nothing but P of A1. So, P of A1 plus P of A2 like this. So, in short notation we write I is equal to 1 to infinity P of AI. So, here also this union of AI we know that A1 union A2 union like this. So, probability of this is equal to probability of A1 plus probability of A2 like this. So, probability of union of AI I is equal to 1 to infinity, this is nothing but summation short notation P of AI whenever they are mutually exclusive. In particular, for two events, suppose A1 A2 belongs to C, probability with mutually exclusive with A1 intersection E2 is equal to phi, then probability of A1 union A2 is nothing but probability of A1 plus probability of A2. So, this is the third property, third axioms. So, this is axiom 1. So, if it satisfies the following, suppose let us write axioms. So, this is axiom 1, this is axiom 2 and this is axiom 3. So, here already it is mentioned. So, axiom 1, axiom 3 it is already mentioned. So, that actually I have written here slowly, so that you can understand clearly. For every element A in class C, P of A is greater than equal to 0. For the sure or certain event S in the class C, probability of S is equal to 1. For any number of mutually exclusive events A1 A2 in C, probability of A1 union A2 union this dot dot is nothing but is equal to probability of A1 plus probability of A2 this. In particular, for two mutually exclusive events A1 and A2, probability of A1 union A2 is equal to probability of A1 plus probability of A2. This is the axiom.